Welcome everybody to GeoHug. So before we do kick off today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from. I live on the beautiful lands of the Gadigal, of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, I am thrilled that we have Ryan Noble joining us today. So Ryan is a senior principal research scientist and the group leader of predictive mineral systems science at the CSIRO. He's been with CSIRO for nearly 20 years, and his current project interests are focused on getting the maximum information from soil samples with the least effort. I love that. And so with all of his expertise, it's going to be absolutely brilliant hearing from him today about 21st century geochemistry, the good, the bad, and the ugly. So this is going to be an awesome session. I hope you all enjoy it. I'll be promoting you all up as panelists throughout the session. You're more than welcome to come on through if you can. You can jump off mute and you'll be able to chat with Ryan directly towards the end. But yes, thank you so much, Ryan, for joining. It is just awesome having you here today.
Yeah, you're most welcome. I'm really excited to be part of the GeoHug community.
Yeah, it's awesome to have you here. I was really curious what got you into geology and geochemistry to begin with.
Yeah, I think mine is not necessarily the standard geology, geochemistry progression. I started in agriculture and zoology, botany, and progressed into soil science, and that sort of led me down the dark side into getting deeper into the ground, and then it was always the applied nature of science that is really what got me into it.
Yeah.
Like I like the applied nature of some of the agricultural research I was doing, but then at the same time, I really liked soil chemistry, and that flowed into you're looking at arsenic from an environmental perspective. Here's a problem. We're using arsenic as a pathfinder for gold deposits. Do you want to look at that in soils? And so, I was quite enthusiastic about seeing what that was and that aspect, and then moved more into the exploration geochemistry side of science. But it's being able to do something, find something, and then see it applied in industry that is what I'm really passionate about. So I love seeing the work that anyone does, or my CSIRO, my colleagues, my team produce something, and then going out to a mine site and saying, we used your technique and we did this, and I love that's the part that I love.
Yeah, I love that. And so what have been some of your other favorite highlights so far in your career journey?
I think for me, it's the diversity of the research I get to do. It's part of why I've loved staying at CSIRO for so long. They'll have to drag me out of here, I think. Because I get to do things like everything from exploration geochemistry near surface and some of the stuff I'll present today, working with looking at gold nanoparticles and things like that in plants, to CO2 capture, modeling for biogeochemical signatures, and also a range of different sciences. And hydrogeochemistry was what I was initially doing in CSIRO when I first started. So I think it's that blend and taking your core knowledge, but being able to adapt it into different fields. That's got me enthusiastic about all the science I do.
Yeah, that's brilliant. I love I can just feel your passion already, so I'm really excited to hear from you today. It's gonna be awesome. I do ask all our guests to bring some of their favorite pet socks, pet rocks. Don't want the socks, no thanks. And knowing you're a bit of a soils guy, I'm very curious what you have for us today.
So I do have I have a rock, so I will share that. But I'll share my. I was going to say I've got that picture. I just got to remember where it is now. It's on the desktop. I'll just find that. I'll share my favourite soil first because it's a little bit unusual, but certainly not the standard thing people present on GeoHug. But I'll put it up there because it is quite striking. So that was my a soil profile that I worked on in part of my master's work. It's not an area that's very popular at the moment because it's in the Kursk Oblast of Russia, which is part of that right where the war between Ukraine and Russia is going on at the moment. But it's a spectacular profile. That's about 3 meters of profile you're seeing there, and you're getting a real dynamic change. You can see it visually in the colors from quaternary sands at the bottom and then windblown loess materials on the top. And because it's in that high productivity agricultural region of Russia, very deep, organic, rich soils. And so I have a real interest in that, but it also drives some of the science in geochemistry that I do, because I really focus on how soil profiles change and the morphology and how that can impact our interpretation of geochemistry. And the other thing that I like about this picture is the crotavinas in it. So you can see all those animal burrows, and you can get an appreciation of how the soil is undergoing bioturbation. So things are moving in that environment, and that's also moving elements and moving our chemistry around. And so you see that with some of those, the dark pockets of organic rich soil that are down 2 or 3 meters in the bottom of that profile, and you're sort of seeing that in action. So that's one of my favorite geochemistry type pets. And then the other one that I brought today in terms of a pet rock, it's just a little one that I picked up, and it is not very exciting to look at. In fact, it's really very bland. But what it is it's taken from right near the first Gossan in the Campbell area, where Roy Woodall and his team first discovered nickel and opened up that whole area from what was initially considered a gold-only part of the Kalgoorlie region, for those that are familiar with that geology. And in 1966, based on prospectors coming into Kalgoorlie office, and Roy and his team went out and checked out what they thought was, what the prospector kept saying was a uranium mineralogy, and it turned out to be, it was bright green and a bit almost luminescent in colour. And that material's been removed from that site, but some of the material's still there of the Gossan. So, I like that rock because it sort of highlights how people with a bit of a different idea and approach to exploration. So again, taking someone else's information and saying, well, maybe there is nickel prospect, or no, maybe this is something we need to go and check out and think differently around this area. Opened up a whole new ore deposits series across a whole area, and basically kickstarted part of WMC's exploration, but also the economics for the Campbell region in general. So to be able to go out there recently and visit that site and see it in person was really nice, and I did some field work out here there recently. So that's my latest favourite.
I love that. That is awesome. You are such a good storyteller too. So thank you for showing us those. And yeah, I'm very excited to hear from you today. So thank you for taking the time to talk to us. If you want to share your screen and we'll get stuck into it.
Some of these slides may be a little older and different. This one even says December 2015, but it's a modification. I'm going to mix it up a little bit today because I wanted to talk around the theme, the good, the bad, and the ugly of exploration geochemistry, because it is something that I'm really quite interested in. I'm enthusiastic about a range of different aspects, but also I like to occasionally get on a soapbox and have a bit of a discussion around some of the practices that we perhaps do or don't do well, and how we can possibly improve those going forward. So it's a bit of a mix. And in full disclosure, I wasn't exactly sure I was doing just a presentation with PowerPoint or whether this was more of a discussion. And so I'm going to go through this presentation. I'm also going to jump because I really want to highlight a couple of the things that I've been talking about more recently, which is around some of the landscape modelling using spectral data and interpretation of that aspect. And I gave a presentation at the IAGS, which Jess was very active in recently, and so I'm going to jump to that presentation as well halfway through because it sort of gives another aspect of the research that I'm really interested in as well. So in terms of the good, the bad, and the ugly, I pinched this theme a few years ago from I think it was Bernd Lodemoser, who gave a presentation when I was starting my PhD. I like the theme, and I think it translates. He was talking about environmental geochemistry, but I thought it really applies well into the exploration geochemistry space. And I will present a number of different bits of information here. So I just wanted to acknowledge some of those project partners and also the people that I have either borrowed imagery from, maybe without authorization in terms of the good, the bad, and the ugly, Hollywood studios. But they'll show up in this presentation as well. So thanks to them. So for those of you that aren't familiar with the movie, I'll just set briefly the main characters, Blondie the good, Angel Eyes is the bad and Tuco is the ugly. And so I use those little motifs in the corners to highlight sort of what the topic is around. But really, it's a spaghetti western. It starts out around sort of the gunslingers competing for a fortune in the West, even though there's the chaos of the American Civil War going on more broadly, probably more to the east, but and I liken that in the exploration sense to the turbulence of exploration cycles, whether it's prices or what's the hot commodities or budgets and all these sorts of things that we constantly have to work around and adjust to. It also was one of the first movies that showed long shots and close-ups, and the opening scene of that movie does exactly that. And I think about that a lot when I think about the scales of exploration that we work in, particularly work that I've been involved with from nanoparticles at the very low, tens of nanometers sort of range, right out to, the continental scale hydrogeochemistry of Australia, where we've taken samples and collected data across Australia, but taken samples at 5 kilometres across hundreds of kilometres of area, and then use that to, hone in on areas of interest and things like that. So we all have to work at different scales, and so that definitely ties into the good, the bad, and the ugly movie itself. There's a lot of stylized gunfights in this, and I liken that to the technical tools that we use. There's always new technology that's coming on board. Some of the stuff that I probably should have talked about today, but I won't, is some of the LIBS mapping technology that's really, hope will really change the way we map mineralogy in the brownfield setting more so, but at nearly real time, and the information we'll be able to gather off that. So that's one technical tool, but I'll touch on perhaps things like the portable devices we have, not just X-ray fluorescence, but now there's, FTIR, spectral sensors. There's a whole range of them now, and LIBS is another one that people use. So we've got more tools than ever and more data than ever to work with. But there's always tension in the frontier, and that's certainly the case in the movie, but it's also tension in the frontiers of exploration. There's a lot of pressure on industry to succeed. There's a lot of pressure on a range of different research providers like us to be active participants, and also to create new technologies and tools. And so these tensions continue, and the aim is to improve exploration success, so downscale or reduce the risk, because it is a risky environment. And in the movie itself, it's a very high risk environment for those that are familiar with it. And I've just got a little slide there sort of highlighting some of the metals prices, and this is the opening shots to the movie. So you've got the distant long shot, and then immediately after that you've got the face appears, and that's that real visual close-up in scales. This talk, or part of this talk anyway, that'll sort of frame this up, and I will spend a bit of time on these topics, is evolved from a talk Peter Winterburn, the late Peter Winterburn, gave at Exploration 17 in every 10 years they have that conference in Canada, and it was around advances in exploration geochemistry. So I'd like to acknowledge the co-authors on that, that is a publication that's available. So Dave Lowy, as well as the other co-author, in the journal Geochemistry, Exploration, Environment Analysis, and it is I think it's open access, so you should be able to get that. And sorry, I've got Teams pop-ups on. The key themes we had in that, and I'm going to spend a bit of time on number 1, 2, and I'm less so on 3, 4, and 5, and I might switch gears a little bit because it is there's quite a few slides, and I want to probably spend a bit more time on the front end. Themes of where there's good, bad, and the ugly: understanding metal mobility, rapid geochemistry analysis, data integration and interoperability, which is something I'm more aware of than actively working in, but it is a big issue for us. Innovation in lab methods, I think a lot of people will have been familiar with those, and I'm probably not going to spend much time on that. And then a little bit on future challenges and frontiers. I might jump back to that one, because that's that is a continued issue that we're going to face. And just to jump ahead, that's really about the geoscience discipline for the future, and the lack of emerging talent, I guess, and not because of there's not talented people out there. It's because a lot of people aren't choosing necessarily careers in geoscience, and also there's not necessarily many universities that are teaching a lot of these things at the moment. So that's a real challenge for us going forward, and a lot of the experience that's now dropping out of the industry as they retire and move on. So I think that is a future challenge, and I may come back to that, but if I forget, at least I've covered it at some level. And the picture there on the right, for those that are maybe confused by that, I am very much a soil scientist. So what I present is and regolith is very biased by my background. I don't work much in hard rocks, and so I put that picture in there because it's the only picture of rocks I tend to present. So for those of you that aren't familiar, there's the Rock, Dwayne Johnson, Chris Rock, and Kid Rock in that picture. So, but we'll move on, hopefully. Although my slide is not wanting to move. There we go. So understanding metal mobility and mechanisms, this has been something I've really worked on quite a lot. And in some ways it's been really good. We have made quite big inroads into understanding metal mobility over the last decades. Some of the earlier Mara projects and some of the other work that's being done in South America and North America from various universities in particular have looked at how metals move through the environment, particularly that transported cover area where we look for anomalies in transported cover, but we don't often understand them. We certainly don't always know how they got there, and we do get a lot of false positives still. So that's one of the challenges. But people have actually spent time looking at some of the mechanisms of metal migration in these settings. So experimental type work. We've looked at things like vegetation studies and how varied they can be. So biogeochemistry is a tool that's used, but we jumped ahead and started using it without necessarily checking some of the fundamentals with how varied are trees. And you can see in that bottom picture, this is a eucalypt in the Widgie area, and you can see that there's 68 ppb gold in the top of this tree, and 2 ppb in the same leaves from the same tree. So understanding that that's how metals are moving in that environment can really change the way we either sample that material or the way we work in that setting. So, and possibly explains things like false positives, which are a real classic challenge. So we've made inroads, but we can certainly improve. And here's just another couple of slides that highlight some of those studies where we've done buried ore and pit experiments. For those that might have seen a presentation I've done in the past years around some of the metal mobility up through transported 2 meters of sand dune. There's I think that's Ravi Anand in the bottom of the pit there, setting this one up. But you can see, we actually did active studies over this and over many years and looked at, what was the flux of the metals and why. And what we found, interestingly, was that where we had free draining materials, we didn't get any anomalies at surface. So this links into, understanding paleo redox fronts or water tables and how that can really change the way metals move through our environment. So there's been some really nice work in that space from a number of different people. And here is one of Mel Linton's papers highlighting, the actual gold particles in some of these eucalypt leaves. And Rob Huff's looking at, I think this was zinc around the Jaguar VMS deposit, and actually proving that it wasn't dust on the outside of leaves, it was actually metals getting into those plant materials. So, there's been a lot of different work on that. Another really nice example was looking at termites. So people have worked on termite mound sampling and thought about that as a sampling media, but had we looked at the termites themselves and how they distribute metals through the termite mounds? And so Aaron Stewart, quite a few years ago, doped up some termites and then imaged them. So I looked at where the metals partition, and you can see here you've got effectively the metals being in the termites' kidneys. So this is the Malpighian tubules of the termites, and you can see where the zinc is partitioned in that environment and the dispersion away from some of those termite mounds. And the bad aspect of this is that we don't often apply it. So even though we know there's variance in the trees, there's different ways metals move through these environments, and sometimes there's limitations. And this is something that I do talk about quite a bit, is, having realistic expectations on where surface geochemistry can work in transported cover. We don't always apply it. And I do see the bad aspect where companies might sample surface soils over 50 meters of transported cover and not get information that they can use. And that's understanding that mechanism and saying, well, actually, this is fairly recently transported. There's not any big, deep-rooted vegetation. I can't see how metals would move through this environment, is a really important consideration. And we don't always take that into account. And hopefully we will do that better. And part of the work that I've been really interested in is trying to highlight those areas in particular. Talk about new techniques a little bit. Partial extraction and gas analyses are things that I've worked on over the years, and sort of talked about why perhaps they, have limitations, and just understanding those rather than saying, here's a technique that's going to be amazing everywhere. Being a bit more realistic is valuable, and is something that we do badly, I think, as a collective. Everyone likes the new tools, they like the excitement of them, and they aren't always keen to put the limitations out there. And partial extractions are definitely one of those areas. So I put these in because there's ways to think about partial extractions that I think have value, or the way you look at them. They're all partial, even the 4-acid ones. So, it doesn't completely digest everything, although it does a pretty good job. And there's classic ones. So I've represented those by Beethoven there in this presentation. 4-acid digestion, aqua regia, some of these extractions that people have used for many years and have a really good understanding of them. They're classics. And then there's the newer music, and literally the new kids on the block there, which are some of these partial extractions that actually have some good reasons to why they can work, but aren't always highly published in terms of comparative studies. And that's a theme that I'll probably come back to a little bit. And time will sort of tell whether they stand up to that. And then I've put Tim Minchin in there for those that are familiar with him. He's a comedic musician and extremely talented, but how it relates here in the partial extraction space is Tim Minchin's classically trained, and in some ways bringing in some classic chemistry understanding, you can produce really quite effective results. And so early on in my CSIRO career, I worked with Cliff Stanley, and we compared some household products basically as extractions for one of these partial extraction applications. And you can see that, there was reasons behind why I think wine, for example, is a really good partial extraction. And if you understand the chemistry of it, they have a lot of organic acids. They operate at a range of different pH levels. And so actually it makes sense that it would be a good partial extraction. And we were able to show that at a range of different experiments where we tested the accuracy and precision. So this was highlighting it's a statistical technique more so than a lot of things, but it was a little tongue-in-cheek and possibly a bit like Tim Minchin. Very skilled musician, classically trained, but having a bit of fun at the same time. And we were doing that to demonstrate, that wine actually was a better partial extraction than things like aqua regia in this setting. The error bars on this are not typical error bars. I will highlight that. That's my chemistry work, not a commercial lab, and normally even I should do better than that. But at the time, my work was not as solid as I wanted it to be. But either way, the anomalous area, and I'll just grab the laser pointer here now, is this shaded zone. And so you're expecting anomalously high chemical results in this setting. And you can see that there with the wine working very effectively. There is publications on this, and for those that are interested, I can either pass on references. I think some of those might be open access, but yeah, there's information out there. You can also go to Cliff Stanley's website. So he's at Acadia University in Nova Scotia, He has an Excel spreadsheet that will do these sorts of calculations for you really quite simply to sort of show which technique gives you the better results. And this is an orientation work, so you have to have an understanding before you did this sort of work where you're expecting your anomalous results. But it's a good way to compare techniques, especially if you're starting out with a new campaign and you want to know which technique I want to use or something like that. This is a nice approach to test. And we don't often see it. So that's the ugly aspect of this sort of geochemistry is we often see one technique. We see things that are highlighted as anomalous, but then we often see things like highlighted in the red circles there where, what's going on? They're anomalous results. They're not really explained. This is my own publication, so I don't mind sort of bagging out the author here. But, typically we would say that, that hasn't worked, even though it looks like in a couple of them, it's got an anomalous result over the mineralization represented by this black bar. And so very often we tend to have a rose-tinted view of these partial extractions, and we will focus on a central area. We will focus on, trying to, convince ourselves that the technique's working when really we should be sort of spending more time thinking about why it perhaps isn't working or where things haven't worked, and is there something we can do about either explaining that or trying to understand it better so that we don't make mistakes by, in this case, running a survey over fairly thick cover and not getting results that you can use. And just highlighting that, there's a range of methods where we've sort of tested this. And this example just shows that exact statistics that we developed. So, this looks like a really positive response over the predetermined anomalous zone. So you can imagine this is your buried ore deposit. Here's your surface geochemistry. This is quite a good result, although this is a false positive, although it looks quite good. And however, if you start to adjust this, so you drop one of those values down to being just background levels, all of a sudden the chance of getting that by sort of random numbers is about 16%. So you don't have really a lot of confidence, even though many people would see this response and argue that the technique has worked very well. And we don't often review those as well as we probably should. So moving on to the rapid geochemical analysis, I'll just sort of highlight a little bit on some of the good aspects of that. As I mentioned, there's a lot of portable devices at our disposal now that are really great about gathering rapid information, and the technology is improving all the time. I haven't highlighted some of the latest ones here, and they're probably older models pictured, but it continues to improve, and the ability to just go out and basically pick up something and get a chemical analysis really quickly has really changed the industry. But again, using them with I guess a degree of I wouldn't say common sense, but with a degree of acceptance that there's still, there's limitations on detection limits, and some of the detection limits quoted are not as strong as perhaps they are advertised, and understanding some of those limitations. So, detectable copper versus non-detectable, people will highlight that as picking up anomalies sometimes, and really it's just above detection limit that it's sort of coming out, and most of that's really lost in the noise. I'm going to move past this one, but rapid sampling and analysis is something that we can do now. We can also adjust things to where we can then, interpret those results in real time and produce almost near-time models, anyway, of surface geochemistry and a range of different things. And we've demonstrated this with the South Australian Geological Survey, where we sampled across Kumpana, so low-impact sampling on a very big and remote area, and sort of using the technology that's available to us to improve the way we go about that. And that's published in the MESA journal back in 2019 it might be. So that's publicly available as well. And I'm happy to provide a list of references maybe in the future if people are interested. That was a video just sort of highlighting the rapid sampling and analysis and sort of that portable lab that we set up on the Nullarbor Plain, just highlighting how you can, going from left to right here, mobile mill or split mill, crush and mill, put into an XRF palette, analyze, and also do spectral mineralogy at the same time, all pretty quickly and roughly just a few hours behind the sampling team. So really useful. However, we also make mistakes, and this was one example where while we were doing a really good example, I'm thinking it might be the next image, shows sort of rapid sampling and analysis, but the team and the ability to infill. So I think we made mistakes on this one. I don't know whether it's showing up in this presentation. So the ability to go back from a model doing your regional space geochemistry and then infill on perhaps a potential target is really valuable. In saying that, even the most experienced people can make mistakes, and because we were rotating sampling and analysis teams, one team was using the XRF with mylar films on it, whereas the other team wasn't for the standards, and it really changed our results. So, and that actually happened to map up with a big geophysical magnetic anomaly. And so we got pretty enthusiastic about this until we actually realized the limitations of what the team had been doing. So that's probably the bad aspect. And I don't think I've got a slide for that. Or maybe I do in the next slide. So, the challenge is sometimes this was our copper map for that same region. So detection limits are problematic in some of these, and also realistic expectations on those detection limits. So while some things might be touted as another example we've done, the technology is really great. Portable PPB are doing gold on portable XRF. Real nice little setup that some of the viewers may be familiar with, and possibly down to, in experimental conditions, down to 10 or 5 ppb in the field, which is amazing. But when you actually tend to use it, probably more realistically is 20 ppb. So if your area has anomalous gold in the ranges of 10 to 20 ppb, it's not going to be effective. And this is a common challenge with people, because they'll see perhaps the experimental work where they've gone and in optimal conditions gone to 5 ppb, and then get out in the field and it doesn't quite perform as well. So again, having those realistic expectations on the elements and how you can use them. And this was the example where I talked about the mylar films just previously, where the team generated, our results were generating this anomaly, and that actually sits over a really large magnetic high or low. Anyway, a strongly contrasting geophysical anomaly. And so the team was really excited that we were picking this up in the surface geochemistry until we realized that there was, problems with the way we were doing our calibration. So even the best operators can make ugly mistakes. And in this case, we were fortunate that we caught it early enough. But there's a lot of similar things that happen with rotating sampling teams as well. And so I think that was the end result of that smoothing of the data. Data access, integration, interoperability. I won't say too much. I might just move through this one a little bit quicker, but we do have a lot more data at our disposal now, more so than ever. And it's important that we have it, but not necessarily, it's a challenge for people to become familiar with it and also to work with it. So I think the newer generations tend to work better. Most of them can code in Python and things like that, and that does really open up a world of new, I guess, discoveries for people, and the ability to work with different data types really well. So I think that's one of the most exciting things I'm seeing from some of my colleagues in particular, that I'm envious of, is their ability to work with data and integrate it at multiple scales and multiple types and these sorts of things. So I'm just going to switch presentations, I think, because I wanted to highlight, and this is just sort of a reflection on some of the work we've been doing more recently, and also does mention on the good, bad, and ugly aspect, again, that common theme of where we've done, there's work to think outside the box, but there's also that unrealistic and impractical ideas, and that's the meaning of blue sky. It can have two different meanings, and I think often we've had unrealistic expectations in some of the geochemistry in particular, and that's one of the things I've worked a lot on, is trying to, I guess, mediate or reset some of the expectations on what we can do at the near surface environment. I'm still very much pro surface geochemistry, but I don't say it works everywhere for everyone. And thinking outside the box is really important for new discoveries. And this comes back to some of that metal mobility understanding. So I've got a couple of slides around that. So my slides don't have the good, bad, and the ugly theme, but talking about the good aspect of where metal migration and understanding that can work. This is some of the work in this is some of the pictures from the Atacama Desert, where people have looked at seismic pumping. So this is where tectonic activity basically squishes groundwater and pushes it up through these porous gravels above and along the tectonic fractures and things like that. And you can actually see it. And this is a publication from Ali Brown recently, where you get these basically, in some cases, metal-rich salts being extruded up to the surface through quite a thick cover. But there's an understanding of how that can happen. You know, if this was not a seismically active area, you would be getting no result at the surface. And so using surface geochemistry in here can be challenging, but perhaps sampling these specific exposures is a way to step around a very large area and understand perhaps which areas might have more metal-rich groundwaters at depth. And so the picture on the left just sort of highlights that in cartoon, where it can work. And there are other things that could also produce geochemical anomalies through deep cover. One of those is soil gases. And so I'll touch on that a little bit more because it is something that I've researched quite a bit. And one of the reasons was because I think it seems like a viable mechanism to explore through deep cover with geochemistry, because we do see gases flux, through the surface, and the pictures of fumaroles, and people in other parts of the world would be more familiar with this than we are in Western Australia. But gases and metals can move through to the surface like that, and we have the ability to detect them. That's the other thing. It's actually not a technology limitation in terms of detecting a gas once you know what you want to look at. But the bad aspect of this is that some of these things have been sort of looked at or touted as pathfinders when there's no evidence of that. So in the cases, we've done work with weathering sulfide ore from known deposits and looked at the gases that are generated, or the gaseous signature, and some of it links perfectly back to work that was done in the late 70s, early 80s with CO2, sulfur dioxide, carbonyl sulfur, or something like that. These compounds are created so they could be pathfinders, but things like hydrocarbons aren't often generated by the weathering of sulfide ores. So we couldn't detect them in weathering, VMS ore from the Yilgarn Craton over a very short distance. So there's no way you could use that approach to find an ore body through tens of meters of cover. And so again, resetting those expectations, and some of this work's been published by my colleague Chloe Plett and others. Those are publicly available. They're open access journals as well, but it just highlights some of those limitations. And so I've got a picture here of the sensor, because this is a very small sensor used to detect cancer in this case, but through a body, a physical, literal body. And so you can detect these things and you can design the sensors to find them. It's just linking it to an actual weathering ore deposit. And so the challenge for gases in particular, and this is where the bad aspect comes in, is that the sulfur compounds and some of the carbon-bearing compounds to a lesser extent are present, but they're at levels that are much lower than the biological bioturbation happening in the near surface. So collecting near surface gases is just getting you a signature of the near surface environment. And so again, understanding that limitation is really important to where you might be able to use them. And perhaps, going deeper in the profile and burying them further there's other work that we could do, and potentially there might be more in the gas space, but at this point at time, we're very restricted on what we can do, and I think that's one of the ugly parts has been where people have pushed through without really a lot of evidence to suggest that they should be using these techniques. I touch on innovation in this presentation, but I'm just going to move through that because one of the things about innovation is it can be done from people from different backgrounds is the way you make big changes. And I think I've seen that in some of my, the work that I've been involved is in when we've brought people from different diversity in backgrounds, not only their own education background, their science disciplines, all those sorts of things. When we've brought people from different backgrounds together, that's where we've made some of the biggest inroads. And I think some of it is because we question some of the more traditional things. So in my own experience, and what's driven a lot of the science that I do has been questioning, why do we always sample it? When people do soil surveys, why are we sampling at 30 centimeters depth when soil morphology varies so much? And can we counter that with other ideas? And I mentioned how I came through, agriculture as a background. One of the things that we would look at in a cornfield is if there was a deficiency in this case, it's the inverse, maybe copper or molybdenum. One of the first things you would look at is looking at some of the other soil properties, particle size, clay, soil pH. Does that explain why things aren't growing properly? And if you think about that in a reverse setting where we're looking for potentially a copper anomaly or a molybdenum anomaly, but we don't measure the soil pH and we don't measure the particle size, and so we don't have this information to draw on. So in a lot of the work that I've been involved with has been bringing in some of these other sciences to try and improve the exploration geochemistry. So I think, I just put a note there about innovation and how, and that's a picture of Roy Woodall as well in the picture. You can see, and he was, a big believer in sort of innovative ideas and bringing teams together with different skill sets to try and find deposits. And, obviously he was very successful with the Cambalda region that I highlighted the rock earlier on, but also with opening, Olympic Dam as another discovery. And what's the other one? Illyria is a calcrete-hosted uranium deposit. So these were big changes and ideas led by diverse teams. So I just wanted to highlight that. I think more often in innovation, though, we work in incremental space where we're making small adaptations. And so I think that's, I like the big ideas and the big impacts of new innovations, but often incremental ones can be just as important. And I've just pictured this one here as, building on the Craystar story. So some may be familiar with that, with the old CRA exploration, basically island hopping around the South Pacific and mobilizing a lab, in this case on a boat with a helicopter, rapid sampling and analysis, and being able to move on. Now, at the time that was an amazing innovation, and we've sort of incrementally improved, done the same sort of thing. So here's pictured lab at rig. I highlighted some of our, helicopter rapid geochemistry in South Australia on the Nullarbor Plains. It's just an incremental change of some of the work that others have done beforehand. And then I highlight some of the scanning technologies and how they're gradually just improving the way we look at things. And yes, there's a picture of my son and his friend looking at a laser, which CSIRO would not endorse having them that close, but it is well protected. And then there's intersectional innovation. This comes back to some of the work I touched on earlier, where that discipline teams and multidisciplines, so bringing in people that were experts in entomology for the studies of insects, botanists that were experts in the plant physiology so that they could understand how the metals were partitioning in those materials, was really important. And some of the same work in other parts of the world has also benefited by not just having hard rock geologists and geochemists working in these settings. It's really benefited from having that different opinions and ideas. So just wanted to highlight that. and this is just some of the experimental work where we've actually looked at metal mobility up through the cover that I wanted to highlight. And then there's sort of a blend of innovation as well, where we do some things incrementally, and then some things perhaps are really changing innovation. And you see, I've got this slide. I mentioned the LIBS work earlier, the laser induced breakdown spectroscopy, and being able to rapidly characterize and generate mineralogy maps of core within hours, maybe behind a drill rig. And this is a high quality SEM image and mineralogy map from a TEMA, for those that are familiar with that. And here's the laser ablation same map. It's actually a bit offset, so you can see that's the same materials going through there. And that's running, at 90 seconds, it's collecting that information. And now the technology is being adapted into, these sort of potentially to core scan this type of information and rapidly produce it. So I'm really excited about those blending of innovations. And again, this brought in physicists to do some of this as a Maya map below it, but the idea of having this extra expertise to produce these sorts of things where, the geologists know how to use this information, they know how to use the mineralogy and how it can guide their exploration, or in this case, it's, understanding maybe an ore deposit and being able to adjust maybe the processing aspect of it. So there's a lot of flow-on effects of this sort of science. So I think we really sort of can see how, blending disciplines can be very powerful in terms of innovation. The bottom map is a Maya map that CSIRO developed, the detector array, and the ability to detect gold particles among really large areas was amazing. And it just told us different stories. So where people had spent, better part of a year or more looking at sulfide grains to understand the gold history in that piece of material, they didn't realize that there was a whole gold story in some of the fluids that were creating, carbonate veins in there, because they couldn't physically map that large area and get the chemistry. So, really valuable tools in terms of how we improve the science going forward. So this is one of those good aspects. Don't really have too many in the way and the bad aspects here. But I guess the bad part is that it's taking a long time to get it functionally behind a drill rig or something similar. But I think that wave of innovation is happening very soon between, this is the LUMO instrument, and Allomission are producing these devices soon. And I think the technology that my colleagues at CSIRO are doing in terms of the processing of this type of data is really going to change the landscape a lot. Satellite imagery is another one that's coming a long way really rapidly. And again, this ties back into that good aspect of data access and interoperability, or at least data access, the ability to integrate some of this data set with other types of satellite systems. So that's one of the challenges. And I don't think I have a slide on that in this presentation, but there's a lot of really great satellites that are now up there collecting really detailed spectral data, but how do we merge those to get the best information and something that's continuous? So working with flight lines in the ASTA maps, and this is pictured on the left here, can be really quite challenging. But you can see the information, in the latest example on Carsten Laukamp's giving me this slide that I used to highlight sort of that. And you can just see there's a lot of opportunities in this space as well. And he has this example where, things like unmapped pegmatites can be really quickly pulled out at near surface. So, just by looking at some of these spectral products, obviously there's pegmatites mapped in the area, and then you look at what the signatures sort of look like in some of these satellite imagery, and you can see, the thing highlighted in pink there is one of those environments that would be worth going and following up to look for pegmatites. And this has been, I guess, enhanced by the drive to explore for lithium. I think this is in the Pilbara area. So, there's opportunities there, but that's a lithium example. But there's going to be opportunities in a whole range of different commodities with these new techniques coming available. And then I'm going to sort of talk more about the work that I'm more familiar with now, and my more recent work. So this is using spatial data to map landscapes. Again, and the driver is to understand geochemistry in landscape context, because I think that's something that we've gone away from, with where we had a lot of expertise in mapping. So, a lot of the geology mapping skills of the past, have translated into regolith mapping skills for some individuals, but often that's not taught as much as it was in university sectors these days. So, the ability to generate a regolith map is really valuable. And one of the ways we can do that, or at least shortcut to improve an understanding of an area, is to use spatial data and machine learning to generate those maps. And so this example just shows satellite image, the actual regolith map from the state geological surveys, and then here's a machine learned map of the same area. And you can see instantly that, we've picked out, in this case, let's see if I've got my laser pointer on. This is a really large sand dune unit. There's outcrops in the dark red, and you can see the detail. This is quite not a big area, but those are 30-meter pixels we're able to map at, and it's these are very remote areas. So to be able to get that sort of information is really valuable. And you can see on the large regional maps, we're not necessarily picking that up, and you can see the fluvial sort of channels here being picked up in the machine learning model. And you can also see if you didn't want to sample in the cover and you wanted to find outcrops in this area that perhaps weren't mapped, this would be a great way to go and find these dark red things are little outcrops in those settings. So maybe not visually so obvious, but if you wanted to cover a large area and perhaps find little outcrops to go and sample, that would be a really great approach to do it. And I think there's a lot that can be gained from this type of work. But my real driver for it is how we interpret geochemistry in those landscape contexts. So going back to the color scheme you sort of saw before, this is an area where there's a landscape model being run. So we've merged spatial data layers, and I don't have that in this presentation. But what we do is merge things like digital elevation model, we merge satellite imagery data, and there's a number of publications on this. So my colleague Anicia Hene has a publication in the Explore article, Explore, which is an AAG publication, and you can get that online for free. And there's also a couple of journal articles coming out pretty soon around this as well, from either her or myself, that touch on the background science behind this. But basically, we merge all these spatial data layers and then ask the computer to cluster it into types, and so it picks things that are similar, and then we color those up. And what it tends to do is pull out things like residual settings as a couple of these redder colors, and then as the cover gets deeper, it tends to pull out. We've adjusted it so it tends to color the deeper cover units in blues. What's really important though in terms of geochemistry, so in this case there's you can see on the right this is part of a really large geochemical survey. You will find the standard geochemical target. So anything above this anomalous threshold, this is the whole data set here. So you can see this is a big data set, nearly 12,000 samples. All the stuff that's above this line is anomalous. That's the stuff that everyone finds easily. And often it is in residual settings. It is in shallow cover. And so the chemistry is elevated for, in this case, copper. But when you start looking at landscape types where perhaps the cover is a bit thicker, the signature is a bit more dilute, those anomalies aren't going to be as obvious. And so here you see in two different landscape types, a whole series of anomalous samples that when you consider that landscape as being, maybe some thicker transported cover, those are the samples that are targets that are overlooked typically, because they're not big concentrations, but they are big concentrations in transported cover. And so, you can start to see here that the red ones, that dark red residual setting, the background here is, I'll just say the valley bottom flatness index, but is basically residual, is dark, and as you get lighter colors, you get into transported cover in this setting. So you would pick out this target, but what you wouldn't pick out necessarily is these samples up here. They are highly anomalous, and hopefully what that does is enables industry to go back and say, well, is there something worth looking at up there? Should I put a shallow drill hole in just to explore because it was on a structure that I thought was interesting, or something else that, you know, got people to sample that in the first place, but perhaps the geochemistry itself didn't stack up. I think that's the thing I really wanted to highlight, and is the value of merging spatial data sets and producing these sorts of landscape maps, but also the ability of bringing, you know, the reason we can do this is because we brought, you know, data scientists and other people into these sorts of projects and had them work with us. And this is just the example I often use to sort of show the progression of, you know, improving the techniques, incremental improvements. So going from an original Geological Survey of Western Australia data set, we reprocess those samples, not much there in terms of gold. Developed a different technique. So again, refining the technique can be an important step. So this was using a technique to separate out the really fine materials, and we were able to improve the detection on those samples, and also pick up, you know, the one known gold mine in the area. This is very broad-based sampling, but you can see there's a lot more information in there, and this is trending into deeper cover. So all of a sudden this greenstone belt, you know, it looks like it does extend, and perhaps there's targets in there. And then finally, by using that landscape analysis, which I just sort of showed an example of before, you're able to find new targets. And in this case, these are, you know, not really great big numbers by any means, but because of the cover and the landscape setting, they are deemed, you know, highly anomalous for that landscape type. So all of a sudden, you're going back to an old sample set, reanalyzing, reprocessing, and being able to generate new targets that may be easily overlooked, or maybe were overlooked by a previous company. So there's a lot of opportunities in shallow cover in particular, and I think that's where it's sort of setting that limitations on the good, bad, and the ugly aspect. Is, you know, there's the good is we're developing techniques. Perhaps the bad is that we overemphasize how thick we can see through cover, or what the thickness of cover we can see through. And the ugly is that we sort of walked away from it. But the benefit, the future aspect, is that we should be able to do improvements on that to generate new targets. And there's a lot of opportunity, and I think I highlight that in the next slide. Yes, where talk about all the samples that are out there, either freely available in, you know, government surveys and things like that, where, you know, you can do this sort of work and reprocess and generate new targets that have been missed. And that's, you know, this is Phil Baker in 2015 sort of compiled this. I think it was 10 million samples in open data. And that's, you know, that's the publicly available stuff. So, you know, you can imagine in what industry hosts and things like that, there's a lot more opportunities to do better quality analysis and interpretation in regions. So I think there's a lot of really exciting future possibilities for exploration in shallow-ish cover. So I think, you know, the 10 to 20, 30 meters of cover is realistic for these sorts of approaches. And so I think there's a lot of excitement in there. And I just wanted to highlight, you know, this XT Apps Gallery, which is where my CSIRO colleagues are putting anything they're developing that we can put into, you know, a little tool for industry to use and make it more accessible. We are putting on our, what we're calling the Exploration Toolkit webpage, and you can go in there and there's apps to download. There's a whole range of different things and different tools. And, you know, Landscape Plus is the one that will generate those landscape maps that are spatially, of those sort of regolith proxy maps in some ways that we're using the spatial data and machine learning to produce. So that will be available hopefully by the end, it's April 2025. We're just putting together that information at the, just, I guess, making it more robust at the moment. And so that will be available to industry. But that's the sort of thing we're doing, where we're developing tools and technologies, and then we're trying to get them out there to industry. So I wanted to put a little plug in there for the research teams at CSIRO that are doing this. And there's a range of different technologies. So drill scanning technology, the hydrogeochemistry work that's Nathan Reed is and his team or colleagues are working on. But that Australian-wide data set is available in there, and comparing your groundwater samples to that Australia-wide data set is really valuable, and you can do that in some of those tools. So yeah, those sorts of things are all there. So I think overall the horizon is certainly much. There's a lot of opportunity there, and so even though perhaps we've gone through some of the good, bad, and ugly aspects of geochemistry, and I haven't spent too much time on some of the other areas that I think could do with some work, but there's also really the horizon is quite bright for geochemistry in particular, and so I'm enthusiastic about that. And I think I will leave it there. But please just, and I've got my contact details there. So for people that have questions, want to follow up on some references and things like that, please reach out. I'm also on LinkedIn as well. Not always that frequently, but frequently enough. And I'm happy to pass on references and other information. I think that's it.
You're amazing, Ryan. Thank you so much for today. Yeah, absolutely awesome. And it was just a privilege having you here. So thank you so, so much.